You're listening to Scientific Giants Who Changed the World. Each episode stands beside one mind and follows a thread of curiosity until it ties to the world we inhabit. Today, we step into a room that was small, hot, crowded, and famously chaotic. A room that smelled of fermenting bananas and hummed with the wings of fruit flies. It was not a cathedral of science, it was a workshop. And inside that workshop, heredity stopped being an abstract idea and became a map you could draw. The man at the center of that transformation was Thomas Hunt Morgan, and the place was known simply as the Fly Room. Morgan was born in 1866 in Lexington, Kentucky, into a world still shaped by the aftermath of the American Civil War. He grew up in a country rebuilding and redefining itself, but his imagination was pulled not toward politics so much as toward living forms. Like many naturalists of his era, he began with observation. He studied animals, he studied embryos. He studied the strange fact that life repeats itself while also producing difference. He trained as a biologist at a time when biology was not yet unified. It was a collection of subfields: anatomy, embryology, natural history. Genetics as a coherent discipline had not yet arrived. One of the most interesting things about Morgan is that he did not begin as a believer in Mendel. When Mendel's work was rediscovered around 1900, it sparked both excitement and argument. Some scientists embraced the idea of particulate inheritance immediately. Others resisted. Morgan was among the skeptical. He worried that Mendelian factors were too neat, too simplistic for the fluid complexity of development. He was an embryologist at heart, and embryology teaches you that life is not just a set of discrete traits. It is a process of unfolding, timing, gradients, and interaction. Morgan suspected that the gene idea might be a conceptual shortcut that ignored the deeper mechanics of how traits emerge. That skepticism, however, is part of what made him powerful. He did not convert because of fashion. He converted because the evidence cornered him. By the time Morgan took a position at Columbia University, he was ready to test heredity with a rigor that would either break Mendelian genetics or force it to mature. He needed an organism suited to experiments that could be repeated quickly with large numbers under controlled conditions. He chose Drosophila melanogaster, the common fruit fly. To modern ears, that choice sounds obvious, because Drosophila became a classic genetic model. But it wasn't obvious then. It was a gamble that a small insect could reveal universal laws. Fruit flies were ideal for reasons that seem almost designed for genetics. They have short generation times, about 2 weeks. They produce many offspring, and perhaps most importantly, they have visible traits that can mutate in ways the human eye can see: eye color, wing shape, body color. If heredity is truly particulate, then with enough crosses and enough counting, patterns should emerge as clearly as Mendel's peas. It is difficult to exaggerate what this meant. Synthetic fertilizer transformed agriculture. Yields rose, food supply expanded. Demographic patterns shifted. Many historians argue that a significant fraction of the world's population today is alive because fixed nitrogen can be produced industrially. In that sense, Haber's discovery is one of the most life-sustaining in human history. And yet, almost immediately, the same ammonia chemistry carried a second implication. Fixed nitrogen is not only fertilizer, it is also a pathway to explosives. Nitrates are central to munitions. In World War I, the ability to produce ammonia helped Germany sustain its war effort, despite blockades that limited access to natural nitrate supplies. Here, the double edge begins to sharpen. Haber was not a passive supplier of a neutral technology. He was deeply involved in Germany's war effort. He believed that in wartime, science should serve the nation. He did not see this as corruption. He saw it as duty. His most infamous role was in chemical warfare. The trench warfare of World War I created a nightmare of stagnation. Armies locked in place, machines grinding bodies from meters of land. Military leaders searched for ways to break the stalemate. Haber became one of the leading proponents of poison gas. The argument for chemical weapons at the time often came wrapped in a moral rationalization. If gas could end the war faster, perhaps it would reduce total suffering. This is a common pattern in human reasoning, using a hypothetical future mercy to justify an immediate atrocity. Haber embraced this logic and helped develop chlorine gas attacks. In 1915, at the Second Battle of Ypres, chlorine gas was released, creating a greenish cloud that rolled into enemy trenches, burning lungs, and turning breathing into drowning. It was a new kind of terror, invisible death carried by air. Haber himself was present to oversee the first large-scale release. This detail matters, because it shows the depth of his commitment. He was not only designing from a safe distance, he was participating in the translation of chemical knowledge into battlefield horror. The personal consequences were severe. Haber's wife, Clara Immerwahr, was herself a chemist, one of the first women to earn a doctorate in chemistry in Germany. She opposed his work on chemical weapons. Their marriage was strained by more than domestic issues. It was strained by a moral rupture. Shortly after the first gas attack, Clara died by suicide, using Haber's pistol. The story is complex and must be treated with care, but it stands as a grim symbol. The cost of aligning science with violence can be paid inside homes as well as on battlefields. Haber returned to work quickly. The war machine does not pause for grief, and neither in his case did the sense of national mission. The world tried to define what had happened. Germany was defeated. Chemical weapons became internationally condemned, even as they remained a temptation. Haber, despite his role, received the Nobel Prize in Chemistry in 1918 for the ammonia synthesis. The award was controversial. Some saw it as honoring a man associated with poison gas. Others argued that the Nobel recognized the fertilizer process, which had immense benefit. This split is the essence of Haber's legacy. You cannot speak his name without two opposing images arriving in the same breath. Franklin's own papers were published in the same issue of Nature, providing crucial experimental support. Yet, in public memory, she was often reduced to a supporting character in someone else's triumph. There is a cruel irony here. Science likes to pretend it is a pure meritocracy of ideas. But science is done by humans, inside institutions, with status structures, with informal networks, with biases that shape what is noticed and what is discounted. Franklin's story is not an exception. It is a clear case where the social world and the intellectual world overlapped, and where the overlap mattered. Franklin left King's College and moved to Birkbeck College, where she did extraordinary work on viruses, including the tobacco mosaic virus and polio-related structures. Her scientific life did not end with DNA. In some ways, her later work shows what she might have become in the long arc of structural biology had she lived longer. But she did not live longer. She died in 1958 at the age of 37, likely from ovarian cancer, possibly related to years of X-ray exposure in an era when safety standards were less developed and less strictly enforced. The basement lab with dangerous X-rays is not a metaphor. It was her daily environment. She worked in conditions that demanded physical risk as part of intellectual pursuit, and she paid a price. When the Nobel Prize for the structure of DNA was awarded in 1962, it went to Watson, Crick, and Wilkins. Nobel Prizes are not awarded posthumously, so Franklin could not have received it, even if the committee had wanted to correct the imbalance. But the fact remains, the public story hardened around the names that received the prize, and Franklin's role became, for many years, a footnote. Then the footnote began to speak. Historians, scientists, and readers looked more carefully. They found not only that Franklin's data was essential, but that her intellectual contribution was deep. She was not merely a technician who produced a useful photograph. She was a structural thinker who knew how to extract meaning from diffraction patterns with disciplined restraint. She understood the grammar of evidence. So how should we remember Rosalind Franklin? We should remember her as a maker of constraints. The double helix model did not emerge from imagination alone. It emerged because the data cornered reality into a narrow set of possibilities. Franklin's work did that cornering. She forced nature to confess its geometry. We should remember her as a scientist whose rigor was, in itself, a kind of courage. Because it is harder to say not yet than it is to say, I think so. And she kept herself honest, even when the race pressured people toward faster claims. We should also remember her as a mirror held up to scientific culture. Her story asks an uncomfortable question. How many discoveries are remembered as the work of a few named geniuses, when in fact they were built from a landscape of labor, and from contributions that were not equally rewarded? Franklin's life reminds us that discovery has a social history, and that the ethics of credit are part of the ethics of science. If you want a final image, picture the diffraction photograph itself, a dark field with a bright X, like a hidden structure insisting on being known. Franklin saw that insistence and followed it with discipline. The world saw it too, eventually. But the delay matters, because it reveals how recognition is not always synchronized with truth. You have been listening to Scientific Giants Who Changed the World. Today, we followed Rosalind Franklin into the basement laboratory where X-rays became a language, where humidity and patience shaped an image that contained the geometry of heredity. In our next episode, we will meet Fritz Haber, a chemist whose work fed billions by pulling nitrogen from the air, and yet also opened the door to chemical warfare, an example of discovery's double edge, sharpened to a terrifying point. Until then, thank you for your attention and your time. This episode was written as a continuous story for the ear, because Franklin's life cannot be honored as a slogan. It has to be experienced as a sequence of choices, constraints, and consequences, until you feel how a pattern on film can carry both truth and tragedy.